Welcome to P. Clark Practical Calculus for the Busy Math Student. Here we're looking at an important concept in definite integration. It's what happens when you have a definite integral with a u-substitution. And this one features the general power rule. Here we're looking at an example of a definite integral that's going to involve a u-substitution. And anytime you encounter this, you have a choice you have to make. There's one of two ways that you can do this. You can either back substitute and evaluate your final answer using the x variable, and we're going to do that first. And then the second option is you can switch everything into the u variable, including the bounds of your definite integral, and just stay there and evaluate it in u. So we'll take a look at that in a little bit here. But for starters, we need to determine the antiderivative, because the fundamental theorem of calculus states that the integral of f of x from a to b is the antiderivative at b minus the antiderivative at a. So I have to figure out what's the antiderivative of x over the square root of 1 plus 2x squared. And hopefully we could spot that there's a du indicator in here. We have a degree 2 in the denominator inside of that radical and degree 1 outside of it. So that tells us we should write up our u sub and see what happens here. So if u is 1 plus 2x squared, then our differential du is 4 times x dx. So this is an almost du case. We're off here by a factor of 4, so we can go ahead and make our du happen here inside the integrand, and then we'll balance on the outside. And that will allow us to rewrite the integral in terms of the u variable. So when we do that, this is our integral, 1/4 times the integral of, this is going to be u to the negative 1/2. We have the square root in the denominator, so we have u to the negative 1/2. That's this part. And then the 4x times dx is the du in the integral. So we're looking at something on the order of 1/4 integral u to the negative 1/2 du. Now if you're going to go back into the x variable, if that's how you think you're going to evaluate and get the actual number for this definite integral, you have two options here. You can either just kind of ignore the bounds on the integral and focus on the antiderivative till you get to the end, or if you want to carry them along, just make sure that you make a note that if I say 0 to 2 here, that's not u going from 0 to 2, that's x. The one thing we don't want to do, and we work with a u sub in a definite integral, is to plug bounds of x into an antiderivative in u, or vice versa. So if we see du on the inside of the integral and we just say 0 to 2, the implication is that u is going from 0 to 2, and that's not what we're trying to say. So that's your choice. Either just kind of forget the bounds and bring them back at the end, or if you're going to carry them through, make a note to yourself that it's not the u variable they're describing. So we go ahead and we do the antiderivative. This is general power rule. So this is going to give us 1/4 times 2u to the 1/2, and the evaluation which ultimately will happen here would be from x from 0 to 2. So we can't do it yet. We're not consistent here in our variables. So in this first option, what we're going to do is to back substitute, just like we did with indefinite integrals, and get the antiderivative in x. So if we do that, it gives us 1/2 times the quantity 1 plus 2x squared to the 1/2. Now I have an antiderivative in x, and I have bounds in x. So I can apply the fundamental theorem and evaluate this thing. If you have a constant multiple out front, we have that factor of 1/2. It's your choice, but it's going to be a common factor. So a lot of times the calculations are easier if you factor it out at the beginning when you go ahead and apply the fundamental theorem here. So ultimately we get 1/2 times the antiderivative at the upper bound. If I put a 2 in there, that gives us 9 to the 1/2, so the square root of 9. And then when we put the lower bound in of 0, we have 1 plus 0 to the 1/2, so the square root of 1. or 1/2 3 minus 1. So we did all that work, and it turns out the area under the curve from 0 to 2 is equal to 1. So that's kind of for most people that are new to the definite integral and the u-sub, that's kind of the way they like to do it. It's a little safer. They just kind of bring everything back into the x variable and evaluate it. We should double check that if we take a look at the graph here. We see we're describing this region here under the curve from 0 to 2, and by the scale there we're stating that that area is 1. That looks pretty reasonable. So that's one option. So let's take a look now at plan B here. When you have a u-sub and a definite integral, there's this option that may or may not work particularly well depending on the case and the function, but it may be easier to switch the bounds into u. So let's go ahead and take a look at this again. So here we take a look at the same integral, and the antiderivative is obtained in the same way. So there's our same u-sub, and the balancing, a factor of 4 on the inside and 1/4 on the outside. And then we can rewrite our integral as 1/4 u to negative 1/2 du. So now what we're going to do is to, instead of integrating and back substituting, we're going to say, well, let's just stay in the u variable and do the whole thing here. And remember, in the u transformation of an integral, there's one decision that's made, and the decision we made was that u is 1 plus 2x squared. So if that's how I got from my integral in the x variable to the integral in the u variable, it stands to reason that if I took the bounds of the integral and ran them through the same u definition, then that should give me the bounds in the u variable. So if my lower bound in x is 0 and u equals 1 plus 2x squared, that's going to result in the lower bound being equal to 1 in the u variable. And if the upper bound is 2, we plug that in and we get u is equal to 9. So my choice I made here was, let's just switch everything over and put the bounds into the u variable too, and then we can just go ahead and finish everything from here. So if we go ahead and state the antiderivative, which we know is 1/2 u to the 1/2, we can evaluate that from 1 to 9. Like we did in the last case when we evaluated x, I'm going to put the coefficient out front and evaluate, and we get the exact same result. It should not surprise us, and ultimately we end up with the area being equal to 1. So if you see it in that case, since the function that we defined as u was fairly simple, it was a polynomial, converting the bounds into u was a nice option there. It doesn't always work that well. Sometimes when you see logs and exponents and things, maybe it's not such a good idea, but something to consider, and it's a choice you can make when you're doing a definite integral that involves a u-sub. Not that you need to go and do this every time, but kind of an interesting point to wrap up this idea of what does a u-substitution look like in a definite integral, is that if we would take this integral in u, 1/4 u to the negative 1/2 from u equals 1 to 9, and we take a look at the graph of that. Let's look at that for a second. The integral in the u variable, 1/4 u to the negative 1/2, then is corresponding to this region under the graph, 1/4 u to the negative 1/2, as u goes from 1 to 9. And so we see here a different looking shape of region, but it does have an area of 1. And so if you kind of compare the two, if we bring back the graph that we used to evaluate an x and compare it to this one, we should be able to convince ourselves that they're actually the exact same size. So here are the two graphs together. The upper one shows what we did first, evaluating in the x variable. So there we back substituted our antiderivative into x, and we evaluated in the original bounds in x. And then the second case, the one on the bottom, is the resulting graph that we get if we switch the bounds into u as well. So regardless which technique we used there, we came up with the same exact area of 1, and it's just a choice that you have to make. But it's kind of neat to see the graphs together. When you're actually doing definite integrals as u-subs, you don't always have to graph what it would look like, the region would look like in u, but it's a nice exercise now and again just to get some idea of exactly what's going on there when we switch the bounds into u as well as the function. To learn more about u-subs or definite integrals or calculus in general, you can look them up in my calculus textbooks available for a nice price on Amazon. If you like the channel here, you can subscribe. Until next time, I'm P. Clark.